everyone, I am Engineer Kamran Khan and you are watching my YouTube channel Learners of Civil Engineering. Guys, today I will be discussing my third lecture, which is related with the subject of foundation engineering, and the title of today's topic is Terzaghi Bearing Capacity Theory. As you guys know that the load of the structure is taken by the foundation, and foundation then transmit that particular load of itself and the superstructure to the subsoil safely without causing any shear failures of the soil, and the resulting settlements produced by the foundation in the subsoil must be within the allowable limits. So in order to just reduce the risk of shear failures and the excessive settlements, we are finding and we should find the bearing capacity of the soil in advance. So what are the different methods available in the literature for the determination of the bearing capacity of soil? This today's lecture is aimed on one of those methods. Now, what are the different methods available for the determination of the bearing capacity of the soil? We are having four methods. The first methods includes the determination of the bearing capacity of soil by using different equations like Terzaghi Bearing Capacity Theory, Merhoff Bearing Capacity Equation, and the Hansen Bearing Capacity Equation. Then you can find the bearing capacity of the soil via different correlations like standard penetration test and cone penetration test. The results of those tests will be utilized via different correlations in order to get the value of the bearing capacity of soil. Then on-site determination of bearing capacity of soil, in which you can go for the plate load test and the pile load test. These tests also give us the value of bearing capacity of soil in field directly. Then presumptive bearing capacity. In this technique, we are taking the bearing capacity of different soils by using different codes available inside each and every country. Like in Pakistan, we can go towards the Uniform Building Code, and over there we can select a particular soil type like SA, SB, SC, SE, SD, etc., and we can find their respective shear strength and the bearing capacity. Now let us discuss the first method, which is known as the Terzaghi Bearing Capacity method or Terzaghi Bearing Capacity Theory. So Terzaghi was the first person who in 1943 gives us an equation, a theory for the determination of the ultimate bearing capacity for shallow foundations. According to his theory, a foundation is shallow if its depth is less than or equal to its width. So that was the definition of the shallow foundation, which was given to us by Terzaghi in 1943. Then later investigator came and they suggested that foundation with depth equal to 3 to 4 times their width may also be defined as shallow foundation. So that is like the modification in the definition of shallow foundation. Till now, you just keep in your mind that for the very first time Terzaghi gives us the evaluation of ultimate bearing capacity for a rough shallow foundation, because that is the biggest assumption of the Terzaghi bearing capacity, that the base of the foundation is rough and the foundation is shallow. Now let us discuss some more assumptions which were basically assumed by Terzaghi while evaluating or extracting or deriving his equation of the bearing capacity. He added that the depth of the footing is less than or equal to its width, which means that the foundation is shallow. Then the foundation is rigid and has a rough bottom. Okay. He added that the base of the foundation is what? It is not smooth but it is rough. Then the soil beneath the footing is a homogeneous and semi-infinite mass. So two things. Number one, the soil beneath this foundation is what? It is homogeneous, which means that it is made up of same types of particles, and it is semi-infinite, which means that the length is infinite but the width is finite. So that is the definition of the semi-infinite mass. Okay. Then he assumed that the foundation is strip foundation, which means that length is more as compared with the width, and the base of the foundation is horizontal, there is no tilting. Okay. And a level ground surface under vertical load, and the soil or the surface beneath the foundation is level, it's not having any slopes, no undulations, etc. Then he assumed the general mode of shear failures of soil. There is no local shear failure and there is no punching shear failure of soil when he was deriving the bearing capacity equation. He also added that there will be no consolidation of the soil. Okay. And the settlement, if any, which will be there in the soil will be only due to the shearing and lateral thrust or movement of the soil. There will be no consolidation settlement. Okay. And the last assumption is about the shear strength of soil. He added that the shear strength of soil will be determined via the Coulomb equation of shear strength or the Coulomb law of shear strength, in which is known as S is equal to C plus sigma tangent phi, where S is the shear strength of soil, C is the cohesion, sigma is the normal stress, and phi is the angle of internal friction. So these are the few assumptions taken by the Terzaghi while deriving his equation. This picture is basically the representation of the failure mechanism which was assumed by Terzaghi, and it is just similar to the failure mechanism of the general shear failure. You can see in this picture, this is the diagram of a strip footing, okay, having width B and length L. It is having some load which has been represented by QU. Okay, this portion is basically representing the ground surface. Okay, and this dotted line is basically representing the base of the foundation. This df is known as the depth of the foundation, df, and q over here is basically known as the surcharge pressure, which is equal to gamma into df, where gamma is the unit weight of the soil and df is the depth of the foundation. He replaced the soil above the bottom of the foundation by an equivalent surcharge pressure. Q is equal to gamma into df, where gamma is the unit weight of the soil above the base of the foundation and df is the depth of the foundation. So assuming a replace of the soil above the base of the foundation by an equivalent surcharge pressure, he also assumed there is no shear resistance of the soil in this particular zone. Now let us discuss the zones of failure below the footing. You can see this A, D, C. This is known as an active wedge, which is also known as zone 1. These other zone like A, D and F and C, D and E, they are known as zone 2 or radial shear zone. This FD, arc FD and arc DE are also known as log spirals, and this zone C, E, G and A, F, H are known as zone 3, which is known as passive Rankine zone. Now in the active wedge, this angle CAD is equal to the soil friction angle, and in the passive Rankine zone, this angle ECG is equal to 45 minus 5 by 2. As you guys know, that angle subtended by any line with the horizontal in the passive Rankine zone is equal to 45 minus 5 by 2. So that is basically the explanation of the failure mechanisms assumed by Terzaghi. This lecture is the representation of the same discussion which I have completed in the previous slide. Like the triangular wedge zone ACD immediately under the foundation is known as active zone, that remains intact and moves downward with the foundation. Then the radial shear zone is also known as a transition zone ADF and CDE, with the curves DE and DF being arcs of a logarithmic spiral. Two triangular passive Rankine zones, which are also known as the linear shear zones AFH and CEG. Now let us derive an equation for the Terzaghi bearing capacity theory. Now in this case we will find the expression of the ultimate load of the foundation, which will be transferred to the subsoil. So this will be achieved by balancing this wedge ACD, which is known as the active zone of the foundation, which basically moves downward with the foundation. So Terzaghi assumes a limit equilibrium approach in deriving his equation. Now what is limiting equilibrium approach? Under this approach, at failure we try to balance the forces causing failure and the forces resisting failure. Okay, so now you can see in this case the force which is causing failure is basically QU, the load of the foundation, and this W, which is known as the weight of the wedge. So these are the two disturbing are the forces which are basically causing the failure. And now you can see this PP, which is the force acted by the passive zone, okay, and this C along the surface of the which is known as the cohesion of the soil. So these are basically the two resistive forces. Okay, so at the limit equilibrium approach we are basically balancing these forces, so it will be like the summation of the forces equal to 0 are the summation of all forces acting on the which will be equal to 0. So solving this particular equation, we can easily find this particular equation, which will be known as Q ultimate CNC plus gamma D NQ plus 0.5 B gamma 2 N gamma, in which this C and C is basically the term due to the cohesion of the cell. This gamma 1 D NQ is basically the term related with the surcharge pressure above the foundation level, and half of gamma B N gamma is basically related with the cell beneath the base of the foundation. Okay, so the first term of the Terzaghi bearing capacity is due to the cohesion of cell. The second term is due to the surcharge pressure or the cell above the foundation level, and the third term of the Terzaghi bearing capacity equation is related with the cell below the foundation level, below the base of the footing. So this is a simplified equation of the Terzaghi bearing capacity theory. Now further we can just elaborate this theory for different foundation shapes. Like for the strip footing, this expression will be equal to CNC plus gamma 1 D NQ plus 0.5 B gamma 2 N gamma, where C is the cohesion, NC, NQ and gamma are basically the bearing capacity factors. Unit weight, gamma 1 is the unit weight of the cell above the foundation base, D is the depth of the foundation, B is the width of the foundation, and gamma 2 is basically the unit weight of the cell below the base of the foundation. If we will modify this equation for the net ultimate bearing capacity, then it will be written in this form: CNC plus gamma 1 D into NQ minus 1 plus 0.5 B gamma 2 N gamma. Okay, like when I was discussing the net ultimate bearing capacity with you guys in my previous lecture, I have added that in the net ultimate bearing capacity we are not taking into account the effect of surcharge pressure. Okay, so this gamma 1 D into NQ minus 1 basically subtract the value of surcharge pressure from this equation. Okay, then this formula will be further modified for the square footing in this form: QU net is equal to 1.3 CNC plus gamma 1 D into NQ minus 1 plus 0.35 B gamma 2 N gamma. This will be rewritten for the case of circular footing in this form: QU net is equal to 1.3 CNC plus gamma 1 D into NQ minus 1 plus 0.35 B gamma 2 N gamma. Now guys, N gamma, NQ and NC, okay, in the previous equation are basically the Terzaghi bearing capacity factors, and they are functions of the cell friction angle only, and they can be easily found out via these formulas, like NQ is equal to e power pi tangent phi into tangent square into 45 plus phi by 2, NC is equal to NQ minus 1 divided by tangent phi, N gamma is 1.8 into NQ minus 1 tangent of phi. Now S gamma and SC are the shape factors. You can see in this particular equation, okay, there is no shape factors, but we can also include the shape factors as well. Like over here, this formula will be rewritten in the form of shape factors like CNC SC plus gamma 1 D NQ S gamma plus 0.5 B gamma 2 N gamma S gamma. Okay, so SQ is 1 for continuous footing, SQ is 1 for square footing, SQ is 1 for circular footing. So that's why we are not writing the SQ, because for all shapes of the foundation the value of SQ will be equal to 1, but the value of SC and S gamma will not be 1 when we basically change the geometry of the foundation. Like SC is 1 for the step footing, S gamma is 1 for the step footing, but SC is 1.3 for the round footing and S gamma is 0.6 for the round footing. Similarly, SC for square is 1.3 and S gamma for square is 0.8. Similarly, SC for rectangular is 1 plus B by L into NQ divided by NC, and S gamma for rectangular is 1 minus 0.4 into B by L. So this is how we are incorporating the bearing capacity factors and the shape factors. Bearing capacity factors are the functions of the soil friction angle, and the shape factors are basically the functions of the geometry of the footing. This is again a method, a chart with the help of which you can find the value of NC, NQ, N gamma, which are known as the Terzaghi bearing capacity factors. Like this curve is basically the curve for the values of NC, this red one is for the value of NQ, and this green one is for the value of N gamma. Okay, if let's suppose the value of the phi is 10 degree, then the value of NC will be also almost 10. Similarly, via the intersection procedure, you can find the values of different bearing capacity factors based on different soil friction angles. Now, as I added that Terzaghi in 1943 basically assumed the general shear failure, but later on his equation was also modified for the local shear failure. Okay, and a new relationship was given to us for the local shear failure. So if you are assuming a local shear failure, then you will use this formula, which is equal to C prime NC prime SC plus Q NQ prime SQ plus 0.5 B gamma N gamma prime S gamma. Okay, so now why this C prime and why this Q prime? This is the expression. Coming from general to local shear failure, you will use the effective cohesion of the soil value, which is represented by C prime, and this is equal to 2 by 3 of C. You will not use original soil friction angle but a modified soil friction angle, like tangent phi prime will be equal to tangent 2 by 3 phi. So this modified friction angle phi prime can be further find out with the help of this equation. Phi prime is equal to tangent inverse into tangent into 2 by 3 phi. There will be no change in the shape factors. Okay, only the bearing capacity factors will be modified because the friction angle for those factors will be modified. Now guys, let us perform few numericals based on the Terzaghi bearing capacity equation. Numerical number 1 is a strip footing 1 meter wide. Okay, so the width of the foundation is 1 meter, is laid at a depth of 2 meter. So the depth of the foundation df is equal to 2 meter in C5 soil having the following characteristics. Calculate the ultimate bearing capacity QF by Terzaghi analysis. Take properties of soil as C is equal to 20 kilonewton per meter square, gamma is 18 kilonewton per cubic meter, and phi is equal to 28 degree. Give Terzaghi bearing capacity factors. Phi at phi 28 degree, we can have NC equal to 32, NQ equal to 18, and gamma equal to 16. For the determination of NC, NQ, and gamma, you can use their chart, this chart. Also, you can use these three formulas. Okay. Now let us solve this numerical. Given B is equal to 1 meter, D is equal to 2 meter, gamma is equal to 18 kilonewton per meter square, phi 28, C 20 kilonewton per meter square, bearing capacity factors NC 32, NQ 18, and gamma 16. Okay. Now since phi equal to 28 degree, so we can assume general shear failure. Now the ultimate bearing capacity. For the ultimate bearing capacity, we can use this equation CNC plus gamma D N gamma D NQ plus 0.5 gamma B N gamma. Okay. So the value of C is 20, NC is 32, gamma is 18, depth of foundation is 2, NQ is 18, 0.5, gamma is 18, B is 1, and gamma is 16. So solving this equation, the value of the ultimate bearing capacity is 1432 kilonewton per meter square. Now let us find the net ultimate bearing capacity. So whenever we are dealing with the net ultimate bearing capacity, then the effect of overburden pressure or the surcharge pressure is neglected. So after neglecting the surcharge pressure, we will get the new value of the net ultimate bearing capacity as 1396 kilonewton per meter square. Now if we will take a factor of safety against shear failure of soil is equal to 3, then we can find the grass safe allowable bearing capacity as QNF divided by F plus gamma D, where QNF is the net ultimate bearing capacity, the value of which is 1396 divided by a factor of safety which we have assumed as 3, and gamma D is basically the overburden pressure. Now if we are dealing with grass, we will take into account the value of the surcharge pressure or the overburden pressure as well. So gamma is 18, depth of foundation is 2. So the grass allowable bearing capacity of the foundation in this case will be equal to 501.33 kilonewton per meter square. Now let us solve the second numerical. The statement is calculate the depth at which the footing 2 meter by 2 meter should be placed to transfer total load of 200 tons with a factor of safety of 3. The soil is sandy, having phi equal to 30 degree and unit weight equal to 2 grams per cubic centimeter. Ground water level is too deep, so we will not take into account the effect of water table while finding the value of the ultimate bearing capacities. Given NQ equal to 22D, N gamma 20, and phi equal to 30 degree. So load coming on the square footing is 200 tons. In kg it will be multiplied with 1000 because 1 ton is equal to 1000 kg. The depth of footing is required. Cohesion is 0 because our soil is sandy soil. Okay, over here it is mentioned that soil is sandy. Phi is 30 degree. Okay, so S gamma for the sphere footing, this is the shape factor, is equal to 0.8 and gamma is 2 grams per cubic centimeter. If we will convert this into the kilogram per cubic meter, it will be equal to 2000. Now the net ultimate stress acting on the foundation Q and F is equal to, you can also represent this with Q and U. Okay, will be equal to CNC plus NQ minus 1 into sigma, which is also equal, this sigma is also known as Q, which is equal to the surcharge pressure, and this surcharge pressure is also equal to gamma into depth of the foundation. Okay, D. So NQ minus 1 into sigma plus 0.5 S gamma N gamma B gamma. C is 0 because the soil is sandy, so the first term has been neglected, plus NQ is 22, sigma is unit weight into depth of the foundation, so gamma over here is 2000 kilogram per cubic meter. D is unknown, plus 0.5 S gamma is 0.8, the shape factor. N gamma is the bearing capacity factor 20. B is the width of the foundation, and gamma is again the unit weight of the foundation. So solving this equation, we will get this value for 2000 D plus 32,000. Now let us just convert this net ultimate bearing capacity into the grass safe bearing capacity. So we will add two things. We will divide the value of the net ultimate bearing capacity by some factor of safety, which in this case again I have taken as 3, and we will add the overburden pressure like gamma prime D. So for 2000 D plus 32,000 is basically the value of Q and F or Q and U divided by 3 plus gamma into D, where gamma is the unit weight of the soil. So solving this equation, we will get 16,000 D plus 10,666.66. Now as we have just utilized all the soil properties, all the loads of the structure, and we have found this safe bearing capacity. Now let us calculate the safe stress or the safe pressure for this safe bearing capacity. Okay, the data for this is also given. The load 200 into 1000 is given, and area is also given 2 by 2. So this will give me a safe pressure, a safe stress, okay, which is equal to the safe bearing capacity as well. Okay, this safe stress is equal to the grass safe bearing capacity. So over here I can write down its value 50,000. Now solving this equation, we can get the value of D is 2.458 meter. So this is how we can find the depth of the foundation if width and other data of the equation is given. Numerical number 3. A RCC column has a square footing founded at a 3 meter depth below the surface of clay soil of average density of 18 kN per cubic meter and a shear strength of 80 kN per meter square. The wall cohesion on the vertical sides of the footing, which is acting over the lower half portion only, may be taken as 1/2 of the shear strength. The total load applied to the soil is 2000 kN. Calculate the size of the footing for a safety factor of 3. Okay, so now the previous case was the case of sandy soil in which C was 0, and this case is basically the case of clay soil in which phi will be equal to 0. Okay, you can see over here phi will be equal to 0 because it is a case of clay. In case of clay there will be no phi, and in case of said, there will be no cohesion. Okay, it is also mentioned that the cohesion is equal to 1/2 of the shear strength of the soil. Shear strength of the soil over here it is mentioned as 80 kilonewton per meter square. So 80 divided by 2 is basically the cohesion of the soil. It is mentioned in the statement. Unit weight of the soil is also mentioned. Gamma is equal to 18 kilonewton per cubic meter. Depth of foundation is also mentioned. D is equal to 3 meter. What we are missing is basically the size of the footing, or it is also known as the width of the footing. Okay, so based on the phi value equal to 0, the bearing capacity factors will be NC is equal to 5.7, NQ1, and gamma 0. Okay, for this you can use that graph and the formulas which I have discussed in my previous slides. Then the value of the net ultimate bearing capacity is equal to CNC plus NQ minus 1 into sigma, where sigma is the surcharge pressure, gamma into dF, plus 0.5 S gamma N gamma B into gamma. So the value of C is 40, NC is 5.7, NQ minus 1, NQ is 1, so 1 minus 1 is 0, 1 minus 1 is 0. So this second factor has been gone. The third factor, in the third factor again the value of N gamma is 0, so the third factor has also been gone. So in this case the contribution will be only due to the first term of the bearing capacity equation, which is CNC. So solving this CNC, we will get the value of the net ultimate bearing capacity as 228 kilonewton per meter square. Now converting this into the grass safe bearing capacity, we will divide the net ultimate bearing capacity by some factor of safety, and we will add the effect of overburden pressure. So the value of the net ultimate bearing capacity is 228 divided by the factor of safety. In this case we have taken as 3, gamma is 18 given in the statement, D is 3 given in the statement. We will get the grass safe bearing capacity as 120 kilonewton per meter square. Now the safe stress is basically load divided by the area. So load is given, which is 2000 divided by the area. Area is not given, so it is a square footing, so it will be like B into B, which will be equal to B square. So this safe stress will be equal to the safe bearing capacity, which we have found it over here. So the value of this is 120. Okay, so rearrange this equation, we will get the value of B as 4.08. so this is how we can find the value of the width of the foundation or the size of the foundation. Numerical number 4. A strip footing 1.5 meter wide at its base is located at a depth of 1 meter below the ground surface. The foundation level are gamma 18 kilonewton per cubic meter, cohesion is 30 kilonewton per meter square, phi is 20 degree. Determine the safe bearing capacity using a factor of safety of 2.5. Use Terzaghi analysis and assume soil fails by local shear failure. So now the case is changed. The first case was the numerical number first was simple, in which case we assume the general shear failure, and we find the value of the net ultimate bearing capacity, the grass safe bearing capacity. Okay, and second equation was related with the sandy soil, in which C was 0, and we find out the depth of the foundation. The numerical number third was related with the clay soil or the cohesive soil, in which phi was 0, and we find out the size of the footing or the width of the foundation. Now in this case we will assume the local shear failure. The first three numericals were related with the general shear failure. This numerical is related with the local shear failure. Okay, so in this case we are given with phi equal to 20 degree. Now we will convert this phi into phi prime. Okay, how? By using this equation. Okay, phi prime over here will be equal to, when we will convert this tangent on the other side, so it will become tangent inverse into tangent into 2 by 3 phi. So solving this equation, we will get the value of phi prime is equal to 13.32 degree. So we have modified the solid fraction angle. Okay, originally it was 20 degree, we have modified it to 13.32, and the bearing capacity factors based on the modified solid fraction angle is NC prime is 11.8, NQ prime 3.9, N gamma prime is 1.7. Width of the foundation is given 1.5 meter, depth is 1 meter, gamma is given 18 kilonewton per meter square, phi is 20 degree, C is 30 kilonewton per meter square, NC prime 11.8, NQ prime 3.9, N gamma prime 1.7. Now the expression for the ultimate bearing capacity in case of local shear failure is 2 by 3 CNC prime plus NQ prime minus 1 into phi plus 0.5 N gamma prime B gamma. Okay, so 2 by 3 C value is 30, NC prime is 11.8, NQ prime is 3.9 minus 1 phi over here is gamma into the depth of the foundation. Gamma is 18, depth of foundation is 1, 0.8, N gamma is 1.7, B is 1.5, and gamma is again 18. So solving this equation, we will get the net ultimate bearing capacity is 311.15 kilonewton per meter square. Converting this into the gross safe bearing capacity, we will use the safety factor over here as 2.5 against the shear failure. Okay, and we will add the effect of overburden pressure. So solving this equation, we will find the gross safe bearing capacity is equal to 142.46 kilonewton per meter square. Guys, I hope this video was useful for you related with the Terzaghi bearing capacity equation. Kindly like and share this video, subscribe the channel and press the bell icon so that you will not miss any future updates. Thank you. God bless you.